All right, let's take a look at our lesson for today. We are going to be looking at related rates. Yay! So, related rates are word problems, and word problems aren't necessarily students' favorite thing. So, some students, actually, a lot of students find these a little difficult. So, let's kind of walk through the process. So what we do is these first three steps I call setup. I call this the setup. And so what do we do to set the problem up? So even if you have a hard time continuing through the problem, you should at least get through the setup. So we would draw a picture and we would name the variables and the constants. Okay, we would write down all the numerical information in terms of the symbols that we picked. Like, let's say we are given, height equals something. I don't know, I'm just going to make up another number. Height is 4, and, maybe, I don't know, volume. So the change in volume, dV dt, is -3. I mean, those kind of things. That's what we would do when we write down our numerical information. We write it down in symbol form. Whatever, we have our picture drawn, we've labeled our picture, and we're going to be given information like we might be given height, we might be given a rate of something. This is related rates, and so these problems deal with rates. And the rates are with respect to t. Like they might say, what rate is the radius changing? So that would be, what rate is the radius changing? That would be dr dt equals question mark. What rate is the radius changing? Those are the kinds of ways that we're going to label our figure. Okay, we're going to draw the figure, give it variables. We're going to list our rates and values. Then we want to write down what we're asked to find, which is typically like I did right up here. We want to find dr dt equals question mark. That's how we would write what we're expected to find. It's usually a rate expressed as a derivative, just like I did, like dr dt equals question mark or dh dt equals question mark, whatever we're supposed to find. So those three steps I call the setup. I mean, you can think about them as one whole step if you want. That's just setting the problem up. Once we have the problem set up, then what we need to do is we need to write an equation that relates all those variables together. So we write an equation. There are times where we need extra equations. I call them helper equations. They're helper equations. They're not the main one, but we might need them for clarity on the main equation. So that's certainly possible. We may have just one, or we may have more than one equation. Once we get our equation written, then what we're supposed to do is we're supposed to take the derivative with respect to t, differentiate with respect to t, and every variable gets tagged. It's rare that we actually have a variable for time. I mean, every once in a while we do, but most of the variables are not time. So since we're taking the derivative with respect to time, they pretty much all get tagged, kind of like that, dv dt, dr dt, that kind of thing. The last thing we do is we evaluate. In other words, we throw, I call this, we throw all the numbers in. We throw all the numbers in, and we then figure out what we're missing. If we're missing anything, we might not be. We figure out what is missing, then we go find it. And what do I mean by go find it? Go find it in the word, like in the word problem. It might be disguised somewhere. You might have to do a calculation to find it. There will be other ways to find it. So this is the process that we do every single time we do a related rates problem. Every single time we do these steps. So if you can become familiar with the process and comfortable with the process, then it makes these types of problems easier to work with. Okay. So what we're going to do is we're going to work through some preliminary concept problems, the first two. Okay, the first two problems are kind of setup problems. We're just setting up. It's not asking us to actually find the value. We're practicing setting up. Okay, so a police car approaching a right-angled intersection from the north. They went ahead and drew the picture for us. That was nice of them, wasn't it? That was very nice. They already drew. We aren't always going to have a picture drawn for us, but that's kind of nice. They drew it. So we've got the police car approaching the intersection from the north. So I'm going to draw this line like coming here, right? It's going down from the north. I called this variable A. I mean, you can call it, really pick whatever letter you want. Just label it with whatever letter you want. I just called it A. So the police car, I mean, you could call it P for police car if you wanted to. So A is that variable. So let's see, from the north is chasing a speeding car. The car has turned the corner and is now moving east. So if you have issues with north, out, northeast, southwest, that might be a problem. I don't know. Most people are okay with north, south, east, west. So this car is going east, so it's headed that way, and I called the car B. Again, I don't know, you can call it whatever you want to. You can call it C for car if you want. And so moving east, set up the relationship, then find an equation that shows the related rates of the vehicles with respect to time. All right, notice that they've drawn a dotted line between the vehicles. We're pretending that those points are the vehicles. That's what we're pretending. And so I called this D for distance, because that's the distance between the two vehicles. Again, the variables don't matter. You pick whatever you want. Now, as we look at this figure, so we have the figure drawn, we have to think to ourselves. They haven't given us any numbers because, again, this is just a concept question. We're not actually going to be finding anything. We're just thinking through, how would we set this up? So as I look at the figure, we need to think about what kind of an equation could we use to relate all those variables together. And hopefully Pythagorean comes to mind, right? Pythagorean theorem comes to mind. And so that's the equation that we're going to use to relate all those variables together. They said this was a right angle. So let's do that. So it would be, what, a squared plus b squared equals d squared. And that's what we would do. And then we would go, so we've got our setup. Then we would go to the next step where we take the derivative with respect to t. Okay, so I'm going to go back up at this. Let me see if I can shrink this a bit. Okay, so what have we done? The setup was this part right here. This part was the setup, all the picture drawing and the labeling. That was 1 through 3. This is number 4, where we write an equation that relates the variables. They're wanting us to do step 5, which is differentiate with respect to t. They're wanting us to just go that far and then stop. We don't have any numbers. All right, so let's do that. So we take the derivative of a squared. That would be 2a, and it would be dA dt. We have to tag it. Like I said, we tag everything. Plus, the derivative of b squared is 2b dB dt. Equals the derivative of d squared is 2d dd dt. And that's really all they want us to do. They just want us to get this far and stop. Their requirement was for us to find the equation that shows the related rates of the vehicles with respect to time. That's what this is. They asked that in weird words, but that's what that is. That's what they're asking for. Okay, so I want to pause here for just a moment. So this is the first 5 steps of related rates. Okay, are we okay with this one? We all good? Yes? Okay. So let's look at number 2. They haven't quite completely drawn number 2 for us, which I'm like, gosh, goodness, couldn't you just have finished it for us? They didn't, so we're going to have to kind of fill it out. So let's look. So we have an airplane, which is point A, flying on a horizontal path that will take it directly over an observer, point O. So I'm going to just draw, no, they're talking about the plane. It's going that way. It's flying on a horizontal path. That's going to take it directly over the observer. The airplane maintains a constant altitude. Okay, so what that means to us is that, I'm just going to draw this, we're just going to measure this. This is the altitude. Now again, this is a problem with no numbers. Normally they would tell us what the altitude is. They're not. That's just the altitude. It's some number. It doesn't change. It's a number. So I'm drawing it as solid. It's just some number, the altitude. Okay. Relate all the rates of change of the distance between the observer and the airplane. Oh, they're wanting us to measure the distance between the observer and the airplane. So let's draw that in. So they're wanting this. And again, you don't have to write a dotted line. You can write a solid line. It's okay. And I'm going to call that D for distance. Relate all the rates of change of the distance between the observer and the airplane and the horizontal distance between the two. Okay, so you probably remember from your geometry days the whole, the horizontal, working with the horizontal. Remember all that? So it would, if I want to measure the horizontal distance between the airplane and the person, I basically would be looking at this right here, right? I'd be looking at this distance. This is the horizontal distance between the airplane and the person. That's the horizontal distance. And I called that H for horizontal distance. I don't know, you can call it whatever you want. Again, I called it H. Okay, horizontal distance. So let's see that what they're saying again. So we want the rates of change between the distance of the observer, which is D, and the airplane and the horizontal distance between the two. So I've got 2 variables going on here. 2 variables. I've got H and D. This is not a variable. This is a number, right? That's a number. But at any rate, can you think of this? This is my setup. Okay, so right here, let's just circle. This is the setup. We don't have any numbers. This is numbers 1 through 3. That's my setup. I drew my picture. I put my variables in there. Again, we're a little bit short of that because they don't give us numbers. This is just conceptual. So this is as much as we can do to set up. Now I've got to go to step 4, which is to find an equation that relates those things together. So I need an equation that relates the altitude, which is some number, and H and D. Notice how I can't put numbers for H and D. That is moving, right? Those distances are moving. So, but I can put a number to altitude. So this one, again, nicely is it's a right triangle. So let's utilize Pythagorean theorem. And I'm just going to write altitude squared, whatever that number is, plus H squared equals D squared. Okay, that's my step 4. That's writing the equation that will relate all of the variables together. Step 5 is taking the derivative with respect to t. And let's think about this first one right here. What is the derivative of a number? Any number. The derivative of any number is 0. So that actually goes away, right? That derivative is 0. So then the derivative of h squared is 2h dh dt equals the derivative of d squared is 2d dd dt. And this is what they're asking for, is a formula that relates the rates together.
What did you say about altitude going to 0?
So altitude, we don't know what the number is, but let's just pretend, let's say the number is 500 miles, or that might be too big. So I don't know, 500 something. And so when we take the derivative of this, it turns it to 0. So the derivative with respect to t of that is 0. So this just becomes 0 plus that stuff right there. So it just disappears because it's a number. Okay, are we okay? All right. So let's look at our next problems, which actually, they have numbers in them. So this is a bit of a step, And so number 3 says, a cylinder filled with water has a radius of 4 feet and a height of 11 feet. Water is being drained from the container such that the height is decreasing at 0.1 feet per second. How fast is the volume of the water in the container changing? Okay. So I need to draw a cylinder. We need to draw a cylinder that we're doing our setup. Okay, so I've got my cylinder. Here's my cylinder. My cylinder has a radius of 4 and a height of 11. Okay, we okay so far? Radius 4, height 11. Water is being drained from the container. Water is volume, right? Water would be measured with volume. Water is being drained from the container such that the height is decreasing at 0.1 feet per second. So dh dt is decreasing. Decreasing means it's negative. Negative 0.1 feet per second. Okay. How fast is the volume of the water of the container changing? So we would say dv dt equals question mark. This is my setup right here. That's my setup. Now I'm not quite done because I need to draw water in my container. Because that's, the water is, let's just pretend the water's right here. The water's right here. Okay? That's the water. And this part right here is actually the height of the water. Right? That part is the height of the water. Okay, so it wants us to, let's look at what we've got so far. We need height. It's talking about height, and this gives us a rate for height, and it wants the rate for volume. So we need some kind of volume formula that will relate all that stuff together and that has H in it. You with me? Some kind of formula. So we need a volume for a cylinder. Hopefully we remember that from our previous math classes, volume of a cylinder. V equals pi r squared h. Okay. The radius of the cylinder. Is the radius of the cylinder going to change? Isn't it always going to be 4? Right? It's just, the cylinder isn't shrinking or growing. It's going to be 4. So I'm going to change this to V equals, let's see, 4 squared would be what? 16 pi h. Okay, that is because R is a constant. That's the only reason I'm allowed to put it in. R is a constant. Which variables are remaining constant? Well, R is a constant. I'll just move this down here. R is a constant. And we did. We replaced it. I guess I got a little bit too excited. They wanted us to put it here. That's fine. Okay. So we replaced it. Write an equation. So let's take the derivative. And of course, if we need to do the chain rule, we're going to have to do the chain rule, but we're always going to have to tag, ladies. We always have to tag. So the derivative of v is dv dt equals the derivative of 16 pi h. No, pi is not a constant, right? It's a number, 3.14, blah, blah, blah. So I take the derivative and I get 16 pi times 1 dh dt. That's the equation. And that's how far we've gone so far from all the other problems. We've only gone to this step. We've just gotten our equation with the derivatives and we stopped. The very last thing that we do is put numbers in. Why did what become 0? Oh, because it's attached to the h. It's a coefficient of the h, so it's not allowed to go away. It would be like if you took the derivative of 3x, what would you get? You would get 3. See how the 3 doesn't go away? So if you take the derivative of 16 pi h, then you get 16 pi. That doesn't go away. Okay? So now we sub in the numbers that we know. We want to know dv, and let me shrink this a little bit. We want to know dv dt. That's why we don't have that one yet. 16 pi. dh dt, they said, was negative 0.1. And so we finish that out, and we get dv dt is negative 1.6 pi. And our units would be feet per, what is it? Second squared. And if we had a calculator, it would be about negative 5.0265. All right, so with this number 3, I need to switch. It's the volume, the rate of the volume. It's not like acceleration. So it's actually feet cubed per second, or our units on number 3. It should be feet cubed per second since it's a volume measurement. All right, so let's look at number 4. On this scenario, let's see, we have Ashanti and Kale meet at Starbucks. They're going home. She heads north at a rate of 80 yards per minute, and he heads east at a rate of 110 yards per minute. After 15 minutes, at what rate is the distance between them changing? Okay, so let's draw, well, of course, we need to draw a picture. We're going to do our setup first. So let's put, we're going north. Okay, and I labeled that X just because who knows why. I don't know. You can label it any variable you want. You could even call it, let's see, who's going north? You could even call it A for Ashanti if you want to. So we're going north, and our rate is dx dt equals 80. Then Kale heads east, so we'll go east. And I labeled that Y. And let's see, what do we have? So that rate, dy dt equals 110. Okay, so let's see if we have, so at what rate is the distance between them changing? So we need to measure the distance. We'll just pretend that they're at those ends of those lines. So we'll call this, I don't know, I called it Z. Whichever variable you want, I called it Z. Z, we're going to do distance. So we want to know at what rate is the distance between them changing. So dz dt equals question mark. Okay, so this is our setup. And I'll go ahead and, okay, so there's our setup. We have our drawing. We've labeled variables. The rates that we were given, we've labeled them as well. And so now we're ready to do step 4, which is to find an equation that relates all those together. I'm thinking this looks like Pythag as well, right? We have a right triangle. So x squared plus y squared equals z squared. Okay, that's an equation that relates their distance. Let's see, they said Starbucks X. So they labeled X is Ashanti and Y is Kale. So that was their choice. And their distance is Z. Okay, so they kind of picked the variables for us. So our next step would be after we get the equation written, then we take the derivative of both sides. Of course, we're tagging everything with a t. We take the derivative with respect to t. So this would be 2x dx dt plus 2y dy dt equals 2z dz dt. Okay, so let's kind of go through this process again. The setup is where I drew the figure and labeled everything. The step 4 is where we write an equation that relates all the variables together. Step 5 is where we take the derivative with respect to t. And the very last step is where we substitute the values in to, I call that throw the numbers in. We throw the numbers in and figure out what we're looking for. So we want to know, this is what we're looking for. We're looking for dz dt. That's what we're solving for. We should have numbers for everything else. Everything else that's listed should have a number. And if we don't know what the number is, then we have to go look for it. That's basically the easiest way that I have found to do these, is just plug in what you have and go look for what you don't have yet. All right, so here we go. So let's see. We don't exactly know x and y, but let's kind of think through that. It says after 15 minutes. So if they've been walking for 15 minutes, okay, so we'll just start with Ashanti. She's been walking for 15 minutes and she's walking at 80 yards per minute. Wouldn't we be able to find how far she's gone? Right? So we would take the minutes times the rate. And I would have a calculator for this. I did have a calculator for it. I'm not going to pull it up. I've already done the calculations, but you would certainly have a calculator for a problem like this. So I multiply those together and I get 1,200. That's the distance. So that would be x. X is 1,200. So let's look at Kale. Let's see. So it's 15 minutes. So I got the 15. What is the rate? The rate is 110 yards per minute. Again, I just calculate that to get my distance. That gives me 1,650. And this would be my y value. All right, so I've got, let's kind of check off what I have. I've got x, I've got y, I've got dx dt, I've got dy dt. Looks like the only thing that I'm missing is z. The only thing I'm missing right now is z. I'm pretty close to being able to just plug everything in and run with it. But I need to find z. So again, we go back and look. So if I know what x and y is, and I know that this is the relationship between x and y, I can find z, can't I? Can't I do that? If I look, we're going to look at this situation in one point in time. This situation is at 15 minutes. At 15 minutes, we've got this distance and we've got this distance. Shouldn't we be able to find this, right, using our Pythagorean theorem? Okay, so we'll do that. So let's do, again, we would have a calculator. It would be, 1,200 squared plus 1,650 squared equals z squared. So I will just tell you I did put that in my calculator. And what I got was 150 root 185, because, our calculators do that for us. They put it in exact form for us.
So why did you make the derivative formula and why are you using the going back
Okay, so good question. So the Pythagorean is the numbers in a particular point of time. All right, this equation right here that we created, this derivative equation and this equation are fluid. They move, right? So the distance isn't always going to be 1200 and 1650. So what we have to do is we have to do the equation and the derivative in abstract first. We have to do it with variables. We can't actually put numbers in until after we've taken the derivative. Okay, once we've taken the derivative, then we can decide what time period we're looking at. In this case, it was 15 minutes. And then we can apply the actual numbers to sub into the formula. But we can't freeze the formula in place. And we can't do that because it's always moving. We have to do the numbers after we take the derivative. Okay, so that's really, I'm glad you asked, that's a really important concept, is we can't plug numbers in unless the number never changes. And since they're moving and since they're walking, the numbers change every minute, right? Or every second, the numbers are changing. So we cannot use the actual physical numbers until last. Does that make sense? Okay. The more we do, I think the more easier it'll be.
So we take the derivative, but we don't use that equation.
We take the derivative. We are going to use the derivative equation. I'm going to plug into,
So the 150 root 185, that's not our final answer.
no, the 150 root 185 is what z is. Oh, sorry. That's what z is, right? Z is that number. That's what I'm going to put right here. So I've got to solve for dz dt, the one in yellow, by plugging in all the variables need numbers for them. And we're just going back and verifying what those numbers are. Is that okay? Okay. So now let's just plug those numbers in. So again, we would have a calculator. So 2 times 1200 times, let's see, what was that? dx dt, dx dt was 80 plus 2 times cy was 1650 and dy dt was 110. 2 times the z value was the 150 root 185. And then we're solving for dz dt. Okay, so then we use our calculator. I went ahead and multiplied and added all those numbers together. And I got 555000 equals 300 root 185 dz dt. And then dividing, I get dz dt equals, of course it's a decimal number. I guess you could put it in exact form, but if you put it in exact form, it's just going to be weird. If you tell somebody that the distance is changing by, 555,000 over 300 root 185, that would be weird, right? Nobody would really know what you're talking about. So it would be better if we put it in decimal form. So it's really 136.0147, and it's yards per minute. Now I've gone to 4 decimal places because I want you to be able to judge whether you want to round or truncate. Our default is the thousandths. We need 3 decimal places. So in this case, you could have, if you truncated, it would have been 0.014, or if you rounded, it would have been 0.015, and either of those is acceptable. Okay?